Beneath the endless blue expanse that covers 70% of Earth's surface lies a hidden realm of unimaginable power. Here, in the perpetual darkness of the deep ocean floor, forces operate that literally move continents, birth new land, and regulate the very climate that makes life possible. What if the secret to our planet's incredible dynamism doesn't lie in the familiar world of sunlight and atmosphere, but in the alien landscape miles beneath the waves? What if the engine that drives Earth's geological heartbeat, controls its magnetic shield, and maintains its delicate temperature balance operates in complete darkness, powered by the planet's molten core? Tonight, we descend into the abyss to discover how the ocean floor serves as Earth's hidden power plant, a vast network of volcanic forges, magnetic generators, and chemical factories that have been shaping our world for billions of years and continue to determine the fate of all life on the surface. This is the story of the ocean floor's invisible empire and how it powers everything we know about our living planet. In the crushing darkness 2 miles beneath the Pacific Ocean, where the weight of water above would instantly pulverize any surface dweller, something extraordinary awakens from the Earth's depths. Here, where no sunlight has ever penetrated and temperatures should freeze all life into stillness, the ocean floor erupts with volcanic fury that could power entire civilizations. This is not merely geology in action. This is the planet's beating heart, pumping molten lifeblood through underwater mountain ranges that dwarf the Himalayas. Every second, along invisible seams in the ocean floor, liquid rock emerges from Earth's interior at temperatures exceeding 2,000 degrees Fahrenheit, instantly meeting frigid seawater in explosions of steam and chemistry that have continued unabated for billions of years. These are the mid-ocean ridges, Earth's longest mountain chains, stretching for 40,000 miles beneath the waves like geological circulatory systems that literally create new seafloor and push continents apart. But the ocean floor's power extends far beyond these underwater volcanic forges. Deep beneath the sediments lies a magnetic dynamo that generates Earth's protective magnetic field, shielding all surface life from the solar radiation that would otherwise strip away the atmosphere and render the planet as barren as Mars. Here, too, vast networks of chemical reactions process elements essential for life, cycling carbon, sulfur, and nutrients through systems so complex they rival the metabolisms of living organisms. The ocean floor doesn't simply exist beneath the familiar world of surface life. It actively creates and maintains the conditions that make that surface world possible. Every breath of air, every stable continent, every protective magnetic embrace that shelters Earth from cosmic radiation originates in processes that unfold in the planet's deepest, most alien realm. This is the story of Earth's hidden powerhouse, and how the ocean floor continues to engineer the planet's destiny from the darkness of the abyss. The revelation of the ocean floor's true power began with humanity's first tentative steps into the abyss, a journey that would ultimately rewrite every assumption about how planets function and evolve. For centuries, the deep ocean remained Earth's greatest mystery, more alien and inaccessible than the surface of the moon. Scientists could only guess at what lay beneath miles of crushing water, imagining static, lifeless plains covered in eternal sediment. The breakthrough came in the aftermath of World War II, when military sonar technology developed for submarine warfare was repurposed for peaceful ocean exploration. As research vessels crisscrossed the Atlantic in the 1950s, their sonar pulses revealed something that challenged every existing model of ocean geography. Vast underwater mountain ranges rising from the seafloor, their peaks often reaching within a few thousand feet of the surface. Marie Tharp, a geologist working at Columbia University's Lamont Geological Observatory, became the first human to truly see the ocean floor through her meticulous analysis of sonar data collected by research expeditions. Working with mountains of depth measurements and acoustic profiles, Tharp began constructing detailed maps that revealed the Mid-Atlantic Ridge, a continuous underwater mountain chain that snaked down the center of the Atlantic Ocean like the planet's backbone, made visible. But Tharp's maps revealed something even more extraordinary than underwater mountains. Running along the crest of the Mid-Atlantic Ridge was a continuous valley, a rift that appeared to split the entire mountain range down its center. This discovery suggested that the ocean floor was not static and unchanging, but actively splitting apart along these underwater ridges, with new seafloor somehow emerging from the planet's interior. The evidence for this radical interpretation came from an unexpected source: the magnetic properties of volcanic rocks scattered across the ocean floor. During the 1960s, oceanographers discovered that these rocks contained tiny magnetic minerals that had preserved the orientation of Earth's magnetic field at the moment of their formation. When scientists mapped these magnetic signatures across the seafloor, they found symmetrical patterns of magnetic reversals spreading outward from the mid-ocean ridges like geological zebra stripes. This magnetic evidence provided the smoking gun that proved the ocean floor was indeed spreading apart at the ridges, with fresh molten rock continuously emerging from the planet's interior to create new seafloor. The implications were staggering. The ocean floors were not ancient, stable basins, but dynamic conveyor belts of rock that formed at mid-ocean ridges and eventually disappeared into deep ocean trenches where they plunged back into Earth's interior. Harry Hess, a Princeton geologist and World War II naval officer, synthesized these discoveries into a revolutionary theory he modestly called seafloor spreading. According to Hess's model, the ocean basins were in constant motion, with new seafloor created at underwater volcanic ridges and old seafloor recycled back into the planet's interior at deep ocean trenches. This process, Hess realized, provided the mechanism that could drive continental drift, the slow movement of continents across Earth's surface that geologists had long suspected but could never explain. The discovery phase culminated with the advent of deep-sea submersibles that could carry human observers directly to the ocean floor. When scientists first ascended to the mid-ocean ridges in vehicles like Alvin, they witnessed volcanic processes that had never been observed before. Underwater lava flows creating new seafloor in real time, hydrothermal vents spewing superheated water laden with dissolved minerals, and exotic ecosystems thriving in conditions that seemed utterly hostile to life. These direct observations confirmed that the ocean floor was indeed the planet's most active geological frontier, a realm where Earth's internal heat engine drove processes that shaped continents, regulated climate, and possibly even gave birth to life itself. The discovery phase had revealed that the seemingly static ocean floor was actually Earth's primary powerhouse, continuously creating new land and recycling old materials through processes that operated on scales of both space and time that dwarfed human experience. Deep beneath the ocean's surface, where crushing pressure and eternal darkness reign supreme, Earth's most powerful geological engine operates with relentless precision. The mid-ocean ridge system represents the planet's largest volcanic feature, a continuous chain of underwater mountains and volcanic vents that circles the globe like surgical scars on the seafloor. Here, the planet's internal heat engine drives processes that literally create new land while simultaneously powering the slow dance of continents across Earth's surface. The volcanic engine operates through a process of elegant geological violence that has continued uninterrupted for billions of years. Deep beneath the seafloor, temperatures exceeding 2,000 degrees Fahrenheit cause solid rock to become plastic and buoyant, rising slowly through the planet's interior like bubbles in a lava lamp. When this superheated material reaches the base of the oceanic crust, it encounters a zone of weakness, the spreading center where two massive tectonic plates are pulling apart with inexorable geological patience. As the plates separate, the upwelling molten rock finds pathways to the surface through networks of fractures and fissures that honeycomb the oceanic crust. The moment this liquid rock encounters frigid seawater, extraordinary transformations begin. The temperature differential, from over 2,000 degrees Fahrenheit to near freezing ocean water, creates thermal shocks so severe that the molten rock solidifies almost instantly, forming distinctive pillow-shaped structures that become the foundation stones of new seafloor. But the volcanic engine produces far more than simple rock formations. The chemical interactions between molten rock and seawater create complex mineral deposits that serve as the planet's primary factories for processing essential elements. Copper, zinc, lead, silver, and gold, metals that form the technological backbone of human civilization, are concentrated and refined through volcanic processes that operate with chemical precision no human technology can match. The scale of this volcanic engine defies human comprehension. Along the 40,000-mile length of the mid-ocean ridge system, approximately 17 cubic kilometers of new volcanic rock form each year, enough material to build a mountain the size of Mount Fuji annually. This continuous creation of new seafloor drives the spreading of ocean basins at rates typically measured in centimeters per year, but the cumulative effect over millions of years literally reshapes the planet's surface geography. The volcanic engine's power becomes most dramatically visible at fast-spreading ridges like the East Pacific Rise, where seafloor spreads apart at rates approaching 20 centimeters per year. Here, the volcanic activity creates underwater landscapes that resemble alien worlds. Lava lakes that glow with internal fire, volcanic chimneys that spew superheated water hundreds of feet into the surrounding ocean, and fields of fresh pillow lavas that form new seafloor in real time. These volcanic processes generate more than new rock. They create the chemical foundation for entire ecosystems that exist independent of sunlight. The interaction between molten rock and seawater produces hydrogen sulfide, methane, and other compounds that serve as energy sources for bacteria that form the base of unique food webs. These chemosynthetic ecosystems, discovered only in the late 20th century, demonstrate that the ocean floor's volcanic engine doesn't merely create geological structures. It creates the conditions necessary for entirely novel forms of life. The volcanic engine also plays a crucial role in regulating Earth's climate over geological timescales. The formation of new seafloor at mid-ocean ridges controls the volume of ocean basins, which in turn influences global sea levels. When volcanic activity increases, more new seafloor forms, reducing ocean basin volume and causing sea levels to rise globally. Conversely, periods of reduced volcanic activity allow ocean basins to expand, lowering global sea levels and potentially triggering ice ages. Perhaps most remarkably, the ocean floor's volcanic engine operates as a massive heat transfer system that helps regulate the planet's internal temperature. The continuous creation of new seafloor provides pathways for Earth's internal heat to escape, preventing the planet's interior from overheating while maintaining the temperature differences that drive plate tectonics and the planet's magnetic field. The volcanic engine of the ocean floor represents far more than geological curiosity. It constitutes the fundamental power source that makes Earth a dynamic, living planet capable of supporting complex ecosystems and maintaining stable conditions suitable for life over billions of years. Beneath the ocean floor lies one of Earth's most critical yet invisible systems, the geodynamo that generates the planet's magnetic field, an electromagnetic shield that has protected life from cosmic radiation for over 3 billion years. This magnetic armor operates through processes so complex and powerful that they transform the planet's liquid metal core into a cosmic-scale electrical generator, creating protective forces that extend thousands of miles into space. The source of Earth's magnetic shield lies nearly 1,800 miles beneath the ocean floor, in the planet's outer core, where temperatures exceed 5,000 degrees Fahrenheit and pressures reach millions of times greater than atmospheric pressure at sea level. Here, liquid iron and nickel move in convective currents driven by heat escaping from the planet's solid inner core, creating a dynamic system that operates like a massive electrical dynamo spinning in the depths of the Earth. But the ocean floor plays a crucial role in this magnetic generation system that extends far beyond merely sitting above the deep dynamo. The seafloor spreading process creates and maintains the conditions necessary for the geodynamo to function efficiently. As new oceanic crust forms at mid-ocean ridges, it cools and contracts, creating thermal gradients that help drive the convective motion in the underlying mantle that ultimately powers the core's magnetic field generation. The magnetic field lines generated by Earth's core dynamo emerge from the planet's interior and arc through space in complex patterns that create an invisible protective bubble around the Earth called the magnetosphere. This magnetic cocoon deflects most of the charged particles in the solar wind. A stream of high-energy protons and electrons flowing from the sun at speeds approaching 2 million miles per hour. Without this protection, the solar wind would gradually strip away Earth's atmosphere, leaving the planet as barren and airless as Mars. The ocean floor contains the most complete record of Earth's magnetic field behavior over geological time, preserving the magnetic minerals of volcanic rocks that formed at mid-ocean ridges. These rocks act like geological tape recorders, capturing the orientation and intensity of Earth's magnetic field at the moment of their formation. By studying magnetic patterns in seafloor rocks of different ages, scientists have discovered that the planet's magnetic field periodically reverses, with magnetic north and south poles switching positions. These magnetic reversals occur at irregular intervals ranging from tens of thousands to millions of years. And the seafloor magnetic record shows that the planet has experienced hundreds of these reversals over the past 180 million years. During the brief periods when the magnetic field weakens and reverses, typically lasting a few thousand years, Earth's protective magnetic shield becomes dramatically less effective, allowing increased cosmic radiation to reach the planet's surface. The ocean floor's role in the magnetic system extends beyond simply recording field reversals. The thermal structure of oceanic crust helps regulate the heat flow from the planet's interior, influencing the temperature gradients that drive convection in the liquid outer core. Changes in seafloor spreading rates can alter these thermal patterns, potentially affecting the intensity and stability of the magnetic field generation process itself. Recent research has revealed that the magnetic field generated by Earth's core dynamo influences ocean circulation patterns through subtle electromagnetic effects on seawater, which contains dissolved ions that make it electrically conductive. The planet's magnetic field interacts with moving seawater to create weak electrical currents that may influence large-scale ocean circulation patterns, potentially affecting global climate regulation. The magnetic shield also plays a crucial role in protecting the ocean floor's unique ecosystems from harmful cosmic radiation. The deep-sea hydrothermal vent communities that depend on chemosynthetic bacteria would be particularly vulnerable to genetic damage from cosmic rays if not for the magnetic field's protection. The magnetic shield thus helps preserve not only surface life, but also the exotic ecosystems that exist in the planet's deepest environments. Perhaps most remarkably, the magnetic field recorded in ocean floor rocks provides evidence that Earth's magnetic dynamo has operated continuously for at least 3.5 billion years, making it one of the planet's longest-running and most stable systems. This extraordinary longevity suggests that the ocean floor and the deep planetary systems it overlies have maintained remarkably consistent conditions throughout most of Earth's history, providing the stable magnetic protection that allowed complex life to evolve and flourish. The ocean floor's connection to Earth's magnetic shield reveals that the planet's most remote and alien environments are intimately connected to systems that make surface life possible, demonstrating that the deep ocean serves not merely as habitat for exotic creatures, but as a crucial component in the planetary machinery that maintains Earth as a living world. Hidden within the ocean floor lies Earth's most sophisticated chemical processing facility, a vast network of natural reactors that continuously refine, concentrate, and redistribute the elements essential for life. Operating at temperatures and pressures that would destroy any human-made chemical plant, these deep-sea systems have spent billions of years perfecting chemical reactions that create the building blocks for biological processes while simultaneously regulating the planet's atmospheric and oceanic chemistry. The ocean floor's chemical factory operates primarily through hydrothermal circulation systems that penetrate deep into the newly formed oceanic crust at mid-ocean ridges. Cold seawater percolates downward through networks of fractures and pore spaces in volcanic rocks, descending several kilometers below the seafloor, where it encounters heat sources associated with underground magma chambers. As this seawater heats up, it undergoes profound chemical transformations that alter both the water itself and the rocks through which it flows. At temperatures reaching 400 degrees Celsius, the heated seawater becomes a powerful chemical solvent capable of leaching metals and minerals from the surrounding volcanic rocks. This superheated fluid dissolves copper, zinc, lead, iron, sulfur, and dozens of other elements from the oceanic crust, creating mineral-rich solutions that rise back toward the seafloor through convective circulation. When these hot, chemically loaded fluids encounter cold seawater at the seafloor, they precipitate their dissolved cargo as mineral deposits that form some of Earth's richest or concentrations. The most dramatic manifestations of this chemical processing occur at hydrothermal vents, where superheated water laden with dissolved minerals erupts from the seafloor in spectacular plumes that can reach temperatures of 400 degrees Celsius. These underwater geysers create chimney-like structures as dissolved minerals precipitate out of solution upon contact with cold seawater, building elaborate mineral towers that can grow several meters tall within months. But the chemical factory's influence extends far beyond the dramatic hydrothermal vents. The vast areas of seafloor between active vents serve as slower operating chemical processing zones where seawater continuously reacts with volcanic rocks through lower temperature processes that alter the chemistry of both the ocean and the oceanic crust. These reactions remove magnesium and sulfate from seawater while adding calcium, silica, and trace metals, fundamentally altering the ocean's chemical composition over geological timescales. The ocean floor's chemical systems play crucial roles in regulating Earth's carbon cycle, one of the planet's most important climate control mechanisms. Carbon dioxide dissolved in seawater reacts with volcanic rocks in the oceanic crust to form carbonate minerals, effectively removing CO2 from the ocean atmosphere system for millions of years. This process of carbon sequestration in oceanic rocks helps prevent runaway greenhouse warming and maintains Earth's climate within ranges suitable for life. The chemical factory also processes sulfur through complex reaction networks that influence both ocean chemistry and atmosphere composition. Sulfur compounds produced by seafloor chemical reactions eventually make their way to the surface, where they can affect cloud formation and global climate patterns. The ocean floor thus operates as a crucial component in the planet's sulfur cycle, helping regulate atmospheric chemistry over geological timescales. Perhaps most remarkably, the ocean floor's chemical processing systems appear to create conditions that may have been crucial for the origin of life on Earth. The temperature gradients, chemical diversity, and mineral surfaces associated with hydrothermal systems provide environments where organic molecules can form and concentrate. Some scientists propose that the chemical factory of the ocean floor served as Earth's first laboratory for life, providing the energy sources and chemical building blocks necessary for the emergence of living organisms. The deep-sea chemical systems also concentrate rare earth elements and precious metals through processes that operate with extraordinary efficiency. Manganese nodules and polymetallic sulfide deposits on the ocean floor contain higher concentrations of copper, gold, silver, and rare earth elements than most terrestrial ore deposits, representing billions of years of chemical concentration and refinement by natural processes. The ocean floor's chemical factory operates on scales that dwarf any human industrial system. The global hydrothermal circulation system processes the equivalent of the entire ocean volume through seafloor chemical reactors approximately every 10 million years, continuously altering the chemistry of both seawater and oceanic rocks. This massive chemical processing system helps maintain the ocean's chemical composition within ranges that support marine ecosystems, while simultaneously creating the mineral deposits that may become essential resources for future human technology. The chemical factory reveals that the ocean floor serves not merely as a passive repository for sediments and volcanic rocks, but as an active, planet-scale chemical processing system that has helped create and maintain the chemical conditions necessary for life on Earth throughout the planet's history. The ocean floor operates as Earth's primary engine for continental drift, a geological force so powerful it can split continents apart, push mountain ranges skyward, and rearrange the planet's surface geography over millions of years. This vast mechanical system transforms the energy of Earth's internal heat into the slow but inexorable motion of massive crustal plates, creating and destroying ocean basins while continuously reshaping the world map through processes that operate with the patience of geological time. The continental drift engine operates through the elegant mechanism of seafloor spreading, where new oceanic crust forms continuously at mid-ocean ridges while old oceanic crust disappears into deep ocean trenches. This conveyor belt system creates the driving forces that push continents across Earth's surface at rates typically measured in centimeters per year, slow by human standards, but capable of moving continents thousands of kilometers over geological timescales. The engine's power source lies in Earth's internal heat, generated by radioactive decay in the planet's interior and leftover heat from the planet's formation 4.6 billion years ago. This internal heat creates convection currents in the mantle, the layer of hot, plastic rock that lies between Earth's crust and core. These convective motions transfer heat from the deep interior to the surface, driving the volcanic processes at mid-ocean ridges that create new seafloor and generate the forces that move continents. At mid-ocean ridges, the upwelling of hot mantle material creates volcanic activity that literally pushes existing seafloor apart as new oceanic crust forms. This process, known as ridge push, creates compressive forces that propagate outward from spreading centers, applying steady pressure to the edges of tectonic plates. While individual ridge push forces may seem small, their cumulative effect across thousands of kilometers of mid-ocean ridges generates enormous forces capable of moving entire continents. The continental drift engine also operates through slab pull, the gravitational force exerted by cold, dense oceanic crust as it sinks back into the mantle at subduction zones. When oceanic plates collide with continental plates or other oceanic plates, the denser oceanic crust plunges downward into deep ocean trenches, creating a powerful pulling force that drags the rest of the oceanic plate along behind it. This slab pull mechanism provides much of the driving force for plate motion and continental drift. The engine's mechanical effects become dramatically visible where oceanic and continental plates collide. When a Nazca plate, a section of Pacific Ocean floor, collides with the South American continent, the oceanic plate's descent into the Peru-Chile Trench creates the volcanic activity and crustal deformation that built the Andes Mountains. The ocean floor's motion thus directly creates some of Earth's most spectacular mountain ranges through the mechanical forces generated by plate collision and subduction. The continental drift engine also operates in reverse, splitting continents apart through the formation of new ocean basins. The Atlantic Ocean formed through this process as the African and South American continents separated over the past 200 million years, with the Mid-Atlantic Ridge continuously creating new seafloor that push the continents apart. This process continues today, with the Atlantic Ocean widening by several centimeters each year as new oceanic crust forms at the spreading ridge. The engine's influence extends to the formation and destruction of supercontinents. Massive landmasses formed when continental drift brings most of Earth's land together into single, giant continents. The most recent supercontinent, Pangaea, assembled approximately 300 million years ago through continental drift processes driven by ocean floor dynamics, then broke apart as new ocean basins formed and existing oceans closed through subduction. The timing and patterns of continental drift profoundly influence global climate by altering ocean circulation patterns and the distribution of land masses across different latitude zones. When continents cluster around the equator, they tend to promote global warming through reduced ice formation and altered atmospheric circulation patterns. Conversely, when continents are distributed across polar regions, They can trigger ice ages by promoting ice sheet formation and disrupting warm ocean currents. The continental drift engine also controls the long-term carbon cycle by regulating the exposure of fresh rock surfaces to weathering processes that remove CO2 from the atmosphere. Mountain building associated with continental collisions exposes large areas of fresh rock to chemical weathering, which consumes atmospheric carbon dioxide and helps prevent runaway greenhouse warming over geological timescales. Perhaps most remarkably, the continental drift engine appears to operate as a self-regulating system that maintains Earth's surface temperature within ranges suitable for liquid water and life. The engine's activity increases when Earth's interior is hotter, leading to faster seafloor spreading, more volcanic activity, and increased CO2 emissions that warm the planet. As the planet warms, weathering rates increase, removing more CO2 from the atmosphere and cooling the planet, which reduces the engine's activity in a negative feedback loop that helps maintain climate stability over geological time. The ocean floor's role as Earth's continental drift engine reveals that the planet's most remote and alien environments generate the geological forces that shape the familiar landscapes of the surface world, demonstrating the profound interconnections between Earth's deepest systems and the conditions that make surface life possible. The ocean floor operates as Earth's primary climate regulation system, a vast network of thermal, chemical, and physical processes that have maintained the planet's temperature within ranges suitable for life for billions of years. This deep-sea thermostat functions through complex feedback mechanisms that link volcanic activity, ocean circulation, atmospheric composition, and global temperature in a planetary-scale regulatory system that responds to climate changes with geological precision. The ocean floor's climate regulatory power begins with its role as a massive heat exchanger between Earth's interior and the surface environment. The continuous formation of new oceanic crust at mid-ocean ridges releases heat from the planet's interior directly into the overlying ocean, warming seawater and influencing global ocean circulation patterns. This heat transfer process helps drive the thermohaline circulation, the global conveyor belt of ocean currents that transports heat from tropical to polar regions and plays a crucial role in regulating global climate. Mid-ocean ridge volcanic activity also releases significant quantities of carbon dioxide and other greenhouse gases directly into the ocean, where they influence both ocean chemistry and atmospheric composition over geological timescales. During periods of increased seafloor spreading and volcanic activity, higher CO2 emissions tend to warm the planet's climate. Conversely, periods of reduced volcanic activity release less CO2, contributing to global cooling and potentially triggering ice ages. The ocean floor's chemical processing systems serve as crucial components in the global carbon cycle, one of Earth's most important climate regulation mechanisms. Chemical reactions between seawater and volcanic rocks in the oceanic crust consume atmospheric CO2 by converting it into solid carbonate minerals that become permanently sequestered in seafloor rocks. This carbon sequestration process helps prevent runaway greenhouse warming by removing excess CO2 from the ocean atmosphere system. The formation and subduction of oceanic crust creates a long-term carbon storage and recycling system that operates over millions of years. Carbon-rich sediments and altered oceanic crust are carried deep into Earth's interior at subduction zones, where high temperatures and pressures eventually release the stored carbon back to the surface through volcanic emissions. This deep carbon cycle helps maintain atmospheric CO2 levels within ranges that prevent both runaway greenhouse warming and complete atmospheric freezing. The ocean floor influences global sea levels through its control over ocean basin volume, which in turn affects global climate through changes in the distribution of land and sea. When seafloor spreading rates increase, the formation of more new oceanic crust reduces ocean basin capacity, causing global sea levels to rise. Higher sea levels increase the area of warm, shallow seas that promote evaporation and atmospheric moisture, generally leading to warmer, more humid climates. Conversely, periods of reduced seafloor spreading allow ocean basins to expand as the oceanic crust cools and subsides, lowering global sea levels and exposing more continental land area. Lower sea levels can trigger climate cooling by increasing the area of land available for ice sheet formation and reducing the area of warm shallow seas that contribute moisture to the atmosphere. The ocean floor's hydrothermal circulation systems play important roles in regulating ocean temperature and chemistry by continuously processing seawater through high-temperature chemical reactors. These systems remove heat from the oceanic crust while altering seawater chemistry in ways that influence marine ecosystems and global biogeochemical cycles. The vast scale of hydrothermal circulation, processing the entire ocean volume approximately every 10 million years, makes this system a significant factor in long-term climate regulation. The magnetic field, generated by processes deep beneath the ocean floor, provides crucial climate protection by shielding Earth's atmosphere from solar wind erosion. Without this magnetic protection, the solar wind would gradually strip away atmospheric gases, particularly water vapor and carbon dioxide, eventually leaving Earth with an atmosphere too thin to support liquid water or moderate surface temperatures. The ocean floor also influences regional climate patterns through its control over ocean circulation. The positions of mid-ocean ridges, deep ocean trenches, and underwater mountain ranges all affect the paths of ocean currents, which transport heat, moisture, and nutrients around the globe. Changes in seafloor topography caused by volcanic activity or tectonic motion can alter ocean circulation patterns and create regional climate changes that may persist for millions of years. Perhaps most remarkably, the ocean floor's climate regulation system appears to incorporate negative feedback mechanisms that help maintain Earth's climate stability over geological time. When global temperatures rise, increased weathering of exposed rocks removes more CO2 from the atmosphere, cooling the planet. When temperatures fall, reduced weathering allows CO2 to accumulate, warming the planet. These feedback loops help explain how Earth has maintained liquid water and moderate temperatures throughout most of its 4.6 billion-year history, despite significant changes in solar brightness and atmospheric composition. The ocean floor's role as Earth's climate regulation system reveals that the planet's most remote environments operate sophisticated control mechanisms that maintain surface conditions suitable for life, demonstrating that Earth functions as an integrated system where deep geological processes and surface climate conditions are inextricably linked through complex feedback networks. At the boundary between the known and unknowable, where crushing darkness meets the planet's molten heart, the ocean floor reveals profound truths about the nature of Earth as a living system and humanity's place within the vast web of planetary processes. These remote depths, more alien than the surface of Mars, yet intimately connected to every breath of air and every drop of fresh water, challenge fundamental assumptions about what makes a planet capable of sustaining life across billions of years. The ocean floor's hidden empire of volcanic forges, magnetic generators, and chemical factories operates according to principles that transcend simple mechanical or chemical explanations. These systems exhibit characteristics that resemble the regulatory mechanisms of living organisms. They respond to environmental changes through complex feedback networks. They maintain stable conditions despite external perturbations, and they have evolved over geological time to become increasingly sophisticated and efficient at supporting life. This revelation forces a reconceptualization of Earth not merely as a rocky planet with life clinging to its surface, but as a deeply integrated system where geological and biological processes are so intertwined that the distinction between living and non-living systems becomes meaningless. The ocean floor demonstrates that life exists not despite the planet's geological violence, but because of it, that the volcanic fury, magnetic dynamo, and chemical processing of the deep seafloor create and maintain the conditions that make surface life possible. The philosophical implications extend to humanity's understanding of resilience and continuity across cosmic timescales. The ocean floor systems have operated continuously for billions of years, maintaining their essential functions through asteroid impacts, volcanic catastrophes, ice ages, and mass extinctions that have repeatedly transformed the surface world. This extraordinary stability suggests that Earth's capacity to support life does not depend primarily on surface conditions, but on deep systems that operate with geological patience and persistence. Yet the ocean floor also reveals the profound interconnectedness of all planetary systems, demonstrating that seemingly remote processes in the deepest parts of the ocean influence everything from global climate to the composition of the atmosphere. Every volcanic eruption on the seafloor contributes to atmospheric chemistry. Every magnetic field fluctuation affects the planet's protection from cosmic radiation. Every chemical reaction in hydrothermal systems influences ocean composition and marine ecosystems. This interconnectedness challenges anthropocentric perspectives that place human activities at the center of planetary processes. The ocean floor reveals that Earth operated as a complex, self-regulating system for billions of years before life emerged on land, and will likely continue operating long after human civilization has passed into history. The deep systems that power the planet operate on timescales that dwarf human experience, measuring their rhythms in millions of years rather than seasons or generations. The ocean floor's role in planetary regulation also raises profound questions about the nature of intelligence and intentionality in natural systems. The feedback mechanisms that maintain Earth's climate stability, the chemical processing networks that concentrate essential elements, and the magnetic field generation that protects the atmosphere all exhibit characteristics that appear purposeful and directed toward maintaining conditions suitable for life. Yet these systems operate without consciousness or intentional design, suggesting that intelligence-like behavior can emerge from complex networks of chemical and physical processes. Perhaps most humbling is the realization that human technological civilization depends entirely on materials and energy sources created by ocean floor processes operating over geological time. The metals and electronic devices, the petroleum that powers global transportation, the minerals that form the foundation of modern technology, all originate from deep-sea volcanic and sedimentary processes that concentrated these resources over millions of years. Human civilization represents not a departure from natural processes, but their culmination and expression through conscious beings capable of understanding and manipulating the materials created by Earth's deep systems. The ocean floor also offers perspective on humanity's environmental impact and responsibility. The same systems that have maintained Earth's habitability for billions of years are now being influenced by human activities through climate change, ocean acidification, and deep-sea mining. Understanding the ocean floor's role in planetary regulation reveals that human activities are not merely affecting surface environments, but potentially disrupting the deep regulatory mechanisms that maintain Earth's stability as a living planet. Yet the ocean floor also provides hope and inspiration for humanity's long-term survival and development. The extraordinary creativity and persistence of deep-sea systems demonstrate that even in Earth's most extreme environments, conditions exist that support complex processes and exotic forms of life. These systems suggest that life and intelligence may be far more resilient and adaptable than commonly assumed, capable of finding ways to thrive under conditions that seem utterly hostile to familiar forms of existence. The ocean floor ultimately teaches that Earth functions as a unified system where the deepest geological processes and the highest expressions of biological complexity are connected through networks of interaction that span the entire planet. In studying these hidden depths, humanity discovers not merely exotic geological phenomena, but the deep foundation upon which all terrestrial life rests. A foundation that has supported the emergence of consciousness capable of understanding its own planetary context. In the crushing darkness of the abyss, where volcanic fire meets frigid water and chemical reactions proceed with billion-year patience, lies the beating heart of a living planet that has nurtured consciousness capable of contemplating its own existence and place in the cosmic order. In the eternal darkness beneath the waves, Earth's hidden powerhouse continues its ancient work, forging new lands, maintaining magnetic shields, processing the elements of life, and regulating the climate that makes consciousness possible. The ocean floor reminds us that we live not merely on a planet, but within one, part of an integrated system where the deepest geological processes and the highest expressions of life are united in the magnificent complexity of a world that powers itself from within.